we are in chapter 14. And so what we're going to be talking about today is we're going to talk about periodic motion first, and then we're going to talk about waves after that. And so let's go ahead and start looking and see what we have here. So a periodic motion is a repeat in a regular cycle. You have a period, which is t, is the time needed for the object to complete one cycle. Amplitude is the maximum distance of an object moves from equilibrium position. And then, sorry, I want to highlight that one. I can get it on here. Okay, simple harmonic motion is any system in which a force acting and restores an object's equilibrium position is directly proportional to its displacement. We're going to talk about what Hooke's law is. It's a spring that exerts a force directly proportional to the distance of the stretch, which is magnitude of force, equals spring constant times the distance stretched or compressed from equilibrium position. K depends on the stiffness and other properties of the spring, and then it shows us how you do the calculation with a graph. You have magnitude of force by newtons on this side, which is our dry, right? Which is our y-axis. Stretch distance, which is on our mix. And then we have a slope of a spring constant, and our K is our rise over our run. The steeper the slope, the larger the K, the spring is harder to stretch. Units are in newtons per meter. Negative signs in Hooke's law indicate that the force is in the direction opposite the stretch or compressed area. A real spring that does not obey Hooke's law would be considered like a rubber band or a spring that stretched too far. Potential energy. Potential energy of a spring equals half of the spring constant times square of the displacement. Example problem that we have. Talks about, to the page, on page 385, says that a spring constant, and it gives you stretches by 18 centimeters of bag potatoes, 56 newtons, and suspends at the end. So X is 18. Our force is negative 56 newtons. We're looking for K and PE of the spring. The first thing we want to do is use Hooke's law to isolate K. So we're going to take alpha y inner. We're going to do a negative, let's go up, negative 56 over 18. And we're going to hit enter. Try again. Alpha y inner, because I have something else on there. A negative 56 divided by 18 meters. So if that's the thing that I have, the best thing that I do, instead of doing the alpha y equals, if I do it this way, linear instead, I will get a negative 311. So that's why I get 310. I think it's 311. I like that one better than 310. So if you got 311, I would have that written down. And then you have to find PE, you're going to do 1/2. So it's alpha y inner 1 over 2. We're going to multiply that by 310. And we're going to multiply that by 0.18. And we're going to square it. And that gives us 5.0 times 10 to the 0 power, which is 5.0. So the first one says, what is the spring constant, a constant of a spring that stretches 12 centimeters? Which the object's weight is 24 newtons hanging. So we're going to take our 24 from our 12 and we get 2.0 times 10 to the second. The spring constant is K is 144, and it compressed at 165 centimeters, which we're going to change that to meters. Spring's potential energy is 1.9 joules. And then number 3 has to do with the spring constant at 56 newtons per meter. How far will it stretch the block 18 newtons hung from the end, 18 from 56, which is 0.32. The challenge asks for the spring constant of 256 newtons, and it stretches by giving a potential energy of 48 joules. Well, we have to times it by 2. That's our challenge there, which would be the square root of that, which would be would be 0.61 meters. The next thing it talks about is a pendulum. A simple pendulum is a simple harmonic motion, also occurs in a swing of a pendulum. So when we're talking about a simple pendulum, we're talking about something that has a mass on the object, which is called a bob, suspended by a spring. And on here we're looking at the force tension, the force gravity, and the force normal. Okay? Period of a pendulum is 2 equals 2 2 times square root of the length divided by the gravitational field. Occurs when the force are applied to vibrating and oscillating objects at the time intervals equal to the period of oscillation. So we have problem 2. And on problem 2, it says a pendulum is stretched 36.9 centimeters and has a period of 1.2. What is the gravitational field? So what we're going to do is we're going to do 2 pi, and we're going to times it by L divided by T2, which will give us 9.78. Question number 5 says, what is the period of the earth of the pendulum with a length of 1.0 meter? So based on that, we're going to do 2 pi divided by 1.0 times gravity, which is 2.0 seconds. Number 6 says, how long must the pendulum be on the moon? Give gravity at 1.6 Newton per kilogram, and you have a period of 2 seconds. So we're going to take our 1.6 newtons per kilogram, times it by our 2 seconds over 2 pi, and we get 0.16 meters. And then on the planet, an unknown value of gravity, the period is 75 meters, and the pendulum is 1.8. And so what we're going to do is flip that to make our 2 pi on top, and you should have 9.1 newtons per kilogram. So section 2 talks about what a mechanical wave is. A wave is a disturbance that carries energy through the matter or space without transferring matter. We have what's called a wave pulse, which is a single bump of disturbance of the traveling through a medium. So you have a string and somebody with a hand pushes it down, and as it does, it moves it back and forth. That is known as a transfer wave. A longitudinal wave is like a spring, and where you take your hand and you make that spring small in the middle and you let go of it, and it vibrates it out. Surface water is the flow in the water of a circular path that is parallel to the direction of travel, and the other is time perpendicular to the direction of the wave traveled. So as the wave goes through, the circulation of the surface wave is going in a circular motion. Wave property. You have your wavelength, which is your lambda. It could be from crest to crest or trough to trough. Your amplitude is from your crest to your center part. Well, the center part, and I highlighted it up here in our very first part, equilibrium position, that's what that is right there. That there is equilibrium position. Okay? And then your wavelength can be both. Amplitude is from your equilibrium position to your crest or your trough. Speed equals V divided by, equals change in D over change in time. Frequency is the reciprocal of a period. So here we have displacement versus the direction of the source. So we have our displacement and the direction of our source, and you can see we get lambda, which is wavelength. When we do displacement versus time, that gives us period. So problem 3 tells us a sound wave has a frequency of 192 hertz and travels the length of a football field, 91 meters, in 0.271 seconds. So the first thing we need to do is write down our variables, which we did. We need to define our velocity. We get 337. The next one is we're going to use a relationship between the wave and velocity frequency, which we got. Then we're going to go through and do our lambda. We're going to do our time, and then we're going to get our answer. So the only one that I'm asking you to do on page 393 is question number 15. 15 says the sound waves produced by a clock chimes 515 meters away at 1.5 seconds. So you're just going to find the V. You just take the distance divided by the time. The next one says the sound wave with a frequency of 436 hertz. What is the period? So, well, we're going to do the reciprocal of the period, which would be that number. And then the last one is the wavelength. You're going to take this number and you're going to divide it by our frequency, and we get that answer there. And that is the end of today.